All right, guys, welcome to session two of chapter nine, traversing. We'll discuss just an example with the open link or open traverse. I'll give you guys a couple, like just an example, so that way we can just kind of have another just visual for what we do with computations with when you have an open one. I believe that video from Pearson does a pretty good job. That first one of the angular misclosure, the traverse angular misclosure, did a pretty good job of discussing what we are looking for when we are computing the angular misclosure, balancing the angles, as well as adjusting for azimuths. It does a pretty good job of defining or explaining all the terms and what we're looking for when it comes to when it comes to traversing subjects. So let's go use this example here. So for an open link traverse, so again, we're going to start off with known coordinates, right, of these benchmarks. And then we have ending benchmarks here that we have known coordinates of. And in between will be our traverse data that we are collecting. So first things first, let's say given the known coordinates, right, we're also given the known azimuths of these two legs. So we have our first azimuth is 30 degrees, 30 minutes, 0 seconds. And then the ending leg is 150 degrees, 30 minutes, 0 seconds. So let's say we run through our numbers here. We have and so we go, all right, so we backside here, or sorry, setup here, backside here. Take our interior angle, it's 314.30.05. And then we run through the setups, close back here, right? And so once we close, right, we get a different result in the ending leg, and we are different by 20 seconds compared to the given data. So then we have to, what we do, step one, balance the angles. So again, our measured was 150 degrees, 30 minutes, 20 seconds. Control was 150, 30 minutes, 0 seconds. So now we have to adjust the angles. Given that there was 4 stations that we set up on, we're going to take that 20 and then we're going to divide it by 4, and we're going to get 5 seconds per station to balance the angles. So now, because we are 20 seconds high rather than 20 seconds low, we have to subtract our 5 seconds from each of our interior angles. So each one of those gets subtracted by 5. And so these would be our new interior angles. All right, so it looks something like this. So we would have, again, our data, but with now the balanced angles. And then we would have match the starting and ending azimuths. All right, so now we would go on to be able to compute those azimuths, just like in the video of that chapter 9 of the traverse angular misclosure. It explains how we do that, right? We come off of that first azimuth, and then we add up our angles, and then we can either, if it's over that 360 rule, we just subtract 360 and get it back inside 0 to 360. And then we just continue to use these interior angles to add until we get back to this closing azimuth, just like in the video. So next step would be step 3, latitude and departures. So again, latitude and departure is the formula of our, latitude is equals L times the cosine of our azimuth, or of our azimuth, and departure is our sine is equal to our L times the sine of the azimuth, right? So in this case, to get this departure, or to get this latitude here, we took the distance of 750 times the cosine of this azimuth, and that gives us this latitude. And then same thing, the sine was the sine of this azimuth, right, times the length of this distance, and we got this departure here. So then we would sum up our latitudes, we would sum up our departures, and that would give us our data for the summation of latitudes, our data for the summation of departures here, and we could compare it to the coordinates, or find the relative linear error of closure. So let's say in this example, come back up to here. we have the northing of B and the northing of A, and we're calling this one here, we're calling this one A, and we're calling this one B. So we have, what we'd be able to do is then take the delta of those two northings, and we would get negative 36.6395, right? And then we would take the summation of our departures. And so we would again get that coordinates here of B, easting B here, and the coordinates of easting A. Sorry, did I say that right? Yeah. So sorry, I'm sorry, I pointed backwards. This would be B, and then this would be, oh, sorry, this is B. Sorry, this is B. Sorry, this is B, and this is A, right? Because we're starting here, and then we're coming back here. So this is our B, this is our A. So then again, we got here, we have that, or the easting of B here, subtracted by the easting of A, and we get 1,588.1074. And so what does that mean? Well, if we look at our summation, that was a little different, right? So we look at it here. This is what we have for coordinate values, and this is what we came up with, the summation of our latitudes, summation of our departures. Well, that's a little bit different there. So now we have to use the error of closure, right? And so how do we do that? Well, we got to go, the error of closure is just taking the deltas of the two, we get 0.2893 error in latitude. And then same thing, went too far. And then same thing here, we got that results. And then from our summation, we get 0.1592 in the error and the departure. Well, what do we have to do to figure out the linear error closure? Well, we take that, those delta results, we got to square them, add them together, and then take the square root of it, and we get 0.3302. Well, relative wise, what does that mean, right? Relative error closure, what does that mean? Well, given that we have a given perimeter of 2,199.91 feet, right, from starting to end, and then we just take that, our relative error divided by that perimeter, we get the ratio of 1/6,662. Not standard, right? We don't meet the standard of 1/10,000. We are less than. So that would mean that we would have to redo our measurements again. We would have to figure out where we went wrong on that traverse, because we are not meeting standards of just the raw data side. All right. But continuing on, for the step 5, you're going to take your delta of your latitude of AB, and that's going to be equal to the summation of latitude times the distance of AB divided by the perimeter. And then same thing for the departure. So again, you have your that 0.2893 times your distance of AB divided by 91. Same thing for the departure, right? And then that would be, then you would get these latitude corrections right here. And then you could apply those to your latitude. You could apply this latitude correction to your adjusted latitude, and apply this departure correction to your adjusted departure. And then you would add up those guys, and then you would be able to come here. And I like this style. You would able to apply those adjusted latitudes to your coordinates and make those your adjusted coordinates, and be able to come up with 0. So again, this is just a recap, but I will post more videos from Pearson, because they are very helpful when it comes to just to give you more technical explanations of this traversing compass rule adjustment. So I will post another different video coming up here a little bit, and we will be discussing what I'm looking for this week's lab. And it's just going to be a big old traverse for my on-campus students. I think me and Evan, I'm going to talk to Evan here shortly and just let him know that, hey, we're going to go with a ginormous traverse around the entire campus, and let's just come off of 2 known distances and then close back on those 2 distances. All right. So, all right, you guys, I will post this. I will talk to you guys later, and we can meet up on the next one. Thanks.